Hello everyone, welcome to my new video on transmission line. I am Dr. Parthakotim Shom, currently working as an assistant professor at Department of ECSR University. So in this video we are going to discuss about basic concepts related to transmission line, and also we will try to solve some problems related to this particular topic. So let us move to the next slide. Now when we talk about transmission line, so the first point that comes into the picture is what is a transmission line. So a transmission line is basically nothing but it is a consist of two or more parallel conductors. Okay, so from construction point of view, we can say that a transmission line is nothing but it is a combination of two or more parallel conductors. Now, what is the functioning of this transmission line? The function of this transmission line is to carry signal or information from source to this load. Okay, on one side of transmission line we will have a source connected, and the other side of the transmission line will have the load connected, and the purpose of this transmission line is to carry information or signal from this source to the load. Now this transmission line, it is commonly used to carry your at low frequency. It is used to carry or it is used in power distribution. Okay, so this is the use of transmission line at low frequencies, and at high frequencies we use this transmission line for communication purpose. We use this transmission line for communication purpose. So these are the two major applications of transmission line. Now this transmission line, it can be of different types. Okay, so the most common type of, or like two of the most common types of transmission line that we see is, one is coaxial cable, where you have a central conductor and then you have another cylindrical conductor which is surrounding this central conductor, and they are separated by some dielectric, which is mostly air or some kind of dielectric material. So this kind of transmission lines are called as your coaxial transmission line, and another type of transmission line is your two-wire parallel conductors. So this is the another type of transmission line. Beside these two types of transmission line, we also have your planar transmission line. Then other than that, we have where above your conducting ground plane. Then we also have microstrip transmission line. So these are some of the common transmission line that are used in day-to-day life for carrying either your power distribution or for communication purpose. Now, a transmission line in electromagnetics, it is usually represented in terms of four parameters, that is your R, L, G and C. Now, what is this R, L, G, C? R is nothing but it is resistance per unit length. Resistance per unit length. Then what is this L? L is nothing but it is your inductance per unit length. Then comes your G, which is nothing but conductance per unit length, and finally your capacitance C, which is capacitance per unit length. So a transmission line, as I said, it is usually represented in terms of these four parameters R, L, G, C, which in short, or which in other way also called as your line parameters. So suppose this is a two-wire transmission line. Now how the question is how these parameters are coming into the picture. So if this is a two-way transmission line, so this is nothing but it is an piece of conductor. So any piece of conductor, like it is never perfect. So whenever current flows through this piece of conductor, electrical energy gets converted in the form of a heat, which is leads to power loss and sometimes drop in voltage. So this is caused, or this phenomenon is represented by assuming the presence of a resistor in series formation. Apart from that, then you like how the L is coming into the picture. That all of you know that when a current flows through where, it automatically creates a magnetic field around it, and because of this magnetic field, it stores energy and it resists sudden change in current. Okay, so that is being represented as a series inductance into this system. Then again, if you see this the setup of this two-air transmission line, this is one conductor, this is another conductor, which is usually separated by either dielectric materials like air or plastic. Okay, so this is the setup of a capacitor. So that's why we assume that there exists a parallel capacitor between two transmission lines. And apart from that, again, all of you know that no insulators are perfect, so there is always a chance that certain amount of power will get leaked from this conductor to this conductor through the insulating medium. So we can assume that there is a conductance which is present between these two transmission lines. So these are the four parameters. This is my R, this is my L, this is my C, and this is my G. Now this transmission line, it is assumed to be made up of not a single RLGC but multiple number of RLGC. Okay, so this form of setup is usually called as your distributed arrangement of RLGC in a transmission line. So in a transmission line, these RLGC parameters, they are not arranged in the form of discrete or lumped elements, rather they are arranged in the form of a distributed pattern, as we have shown in this particular figure. Now this transmission line, or each conductors in this transmission line, it is usually characterized by your sorry, it is usually represented by gamma C, which is the conductivity. Then it is mu C, permeability. uh, we also have permittivity. So these conductors, it is usually represented by these three parameters. Okay, similarly the dielectric medium which is separating these two transmission lines, it is represented by again three parameters: sigma, mu, and epsilon. Okay, so the conductors in the transmission line are being characterized or being represented by these three parameters: sigma, mu, and epsilon. And the dielectric is also represented by sigma, mu, and epsilon. The only difference is that here in the notation of the conductor, we are using this C in suffix, which represents that it is related to the conducting material which is used to construct the transmission line. Also, another point that we need to keep in mind is that here this G is not equals to 1 by R. Okay, this R is the property of the transmission line. Here you can see this R is the property of the transmission line, whereas G is the property of the insulating medium which is separating the two transmission lines. So in terms of dimensions, we can we may see that G is nothing but it is equals to 1 by R, but conceptually they are not same, because G is related to the inducting medium and R is related to the conducting medium. So these are some important properties, and apart from that, like for this transmission line, there are some important relation that LC is equals to mu sigma, and G by C, it is your equals to sigma by epsilon. So these are two important relations related to the transmission line. Now we'll shift our focus in analyzing the behavior of a two conductor transmission line. Okay, so first let me draw the two conductor transmission line. Now a important feature about or information about this two conductor transmission line is that it supports your TEM wave. Okay, a two conductor transmission line, it supports a TEM wave, and important property related to this TEM wave is that for a TEM wave, the electric field and magnetic field expression, they are related to voltage and current, as this electric field this voltage is nothing but we can write it as equals to minus line integral of E dot dl. Here E will be a vector, dl will also be a vector, and current can be written as line integral of H dot dl. Okay, so for, as I said, the transmission line, it will support TEM wave, and for a TEM wave, an important property is that electric field and magnetic field, they are uniquely related to voltage and current through these two equations. So for analyzing the behavior of this transmission line, instead of focusing on the field parameters, electric field and magnetic field, we will shift our focus on these two circuit parameters, voltage and currents. We'll try to solve equations to calculate voltage and current using the principles of circuit theories, rather than uh, focusing on calculating electric field and magnetic field using the concept of field theories, which is your solving Maxwell's equation and then apply boundary conditions and all these things. This basically complicates the process a little bit. So calculating voltage and I using the common principles of circuit theories is a comparatively a convenient process. So we'll be focusing on that side. Okay, so to apply this circuit theory concept, what we'll do is we will divide this line, this complete trans we will divide this complete transmission line into a very small section or small length of del z. Let us assume that this complete length is z, and we are just focusing on this small length del z, because in that small length we can assume voltage and current to remain constant over a certain period of time, and hence we can apply the theories or formulas of circuit theories. So in that case, my this equivalent circuit of the for the small length portion del z will be nothing but it will be something like this. The resistance value will now become R del z, inductance value will become L del z for the small length del z region. Then this capacitance value will be nothing but it will be C del z, and this conductance value will be nothing but G del z. So these will be the line param values of the line parameters. The voltage at this side will assume it is nothing but VZT. So obviously voltage on this side will be nothing but VZ plus del Z comma T. Okay. So current in this branch, if we assume it is IZT, so in this branch this current will be nothing but IZ plus del Z comma T. So obviously through this two branch, what current is flowing, it is nothing but I del Z current is basically flowing through this branch. Okay, so this will be the equivalent circuit for a small incremental length of del z, uh, and if we apply now KCL and KVL laws to this small incremental length of del z, we can get voltage and current equations as, just let me note down the expressions, minus, I'm not getting into the detailed part, del VZ T whole divided by not divided, basically differentiation is equals to r I z t plus L del I z t upon del t, and similarly in terms of current also we'll get del I z t upon del z is equals to g v z t plus c del v zt upon del t. So these two equations combinedly they are called as your telegrapher's equation. These two equations combinedly called as your telegrapher's equation, which is a very popular equation in transmission line, which is a very popular equation related to transmission line. And now our effort will be to solve these uh, two equations to find an expression for voltage and current. Now if we assume harmonic time dependence of voltage and currents in telegrapher's equation, then we can rewrite the telegrapher's equation as d square vs upon dz square minus gamma square vs equals to 0. Similarly, we can also write d square is upon dz square minus gamma square is equals to 0, where this is and vs they are nothing but a phasor form of vzt and izt. Okay, now if we find the solution of these two differential equations, these are nothing but second order differential equations. So the solution of these two differential equations will be nothing but it will be vs as a function of z equals to v naught plus e to the power minus gamma z plus v naught minus e to the power plus gamma z. Similarly for ISZ, we can also get ISZ equals to I naught plus e to the power minus gamma z plus I naught minus e to the power plus gamma z, where gamma is nothing but it is equals to your propagation constant. And the formula for this gamma in terms of line parameters are, it is r plus j omega l into g plus j omega c under root. Okay, now if we see the expression of voltage and current, both these terms have two terms. Both these parameters they have two terms. The first term in the expression of voltage, it represents a forward traveling wave which is propagating along plus that direction, and the second term in the expression of voltage, it represents a wave which is traveling along minus z direction, which is also known as your reflected wave or backward wave. Similarly, this first term it is representing plus z directed wave, and the second term representing minus z directed wave. So this is the solution of these two differential equations. This gamma propagation constant, it is again a imaginary number which can be represented as alpha plus I beta or alpha plus j beta, whatever you call it. So where this alpha is nothing but it is your attenuation constant, and this beta is called your phase constant. So now our instantaneous voltage is represented as Vz of t can be obtained as a real part of Vs into e to the power j omega t, where Vs is nothing but it is a function of z. So ultimately what we'll get is V naught plus e to the power minus alpha z, where alpha is nothing but it is attenuation constant cos omega t minus beta z. Beta is nothing but my phase constant, plus v naught minus e to the power plus alpha z, and again cos omega t minus beta z. Okay, so this is the expression of instantaneous voltage on a transmission line, which is nothing but function of both position and time. Similarly, we can also write the expression for current IZT, which will be equals to I naught plus e to the power minus alpha z cos omega t minus beta z in the same form. Okay, now again you can see in this term we have in this equation we have two terms. First is this v naught e to the power minus alpha z cos omega t minus beta z, which is representing a plus z directed wave. Okay, and then we have the second term v naught minus e to the power alpha z cos omega t minus beta z. It represents a minus z directed wave. Okay, so like this we can, how we can understand that this is a plus z direction wave. So here you see, if it's a plus z direction, we are getting e to the power minus alpha z, and here we are getting a minus beta z term. Similarly, here it is minus z directed because we have in e power plus z, and here also sorry, I made one mistake. It will be actually cos omega t plus beta z, so this term will be plus beta z. Okay, so for example, in that way we can write that a minus y directed wave will be nothing but e to the power alpha y into cos omega t plus beta y. Okay, and similarly plus y direction wave will be minus e to the power minus alpha y cos omega t minus beta y. So it will depend on like what direction of wave we are assuming. Here we assumed our transmission line is aligned along the z axis, so that's why we are, the direction of wave propagation is also we are considering in the term of in terms of z coordinates. If we assume that our transmission line is aligned along y axis, so these terms will this z term will also get changed accordingly. Okay, so this is the expression of instantaneous voltage. Similarly, we can get instantaneous expression of current, which is nothing but it is a sum of two terms. The first term represent a positive directed positive z directed wave or forward wave, and the second term represents negative z directed wave or my minus wave. Now, related to transmission line, we'll study few important parameters. One such first important parameter is called as characteristic impedance. This characteristic impedance, it is represented using the symbol Z naught. And this characteristic impedance, if we look at the definition of this line characteristic impedance, it is nothing but it is ratio of positively traveling voltage wave to the current wave at any point on the transmission line. And how to calculate this Z naught? Mathematically, we can calculate the Z naught in terms of line parameters, which is nothing but square root of R plus J omega L divided by G plus J omega C. Okay, so this Z naught is also a complex number, and it can be represented as R naught plus J X naught, where R naught is the real part of Z naught and X naught represents the imaginary component of the Z naught. Now, till now we have discussed about our lossy transmission line. So now we will shift our focus to lossless transmission line. Now, what is a lossless transmission line? A lossless transmission line is something which has infinite conductivity for the conductors. So sigma c is almost equals to infinity, and the dielectric medium between the two conductors is perfectly lossless. So this sigma will be equals to almost equals to 0. So such a line will be called as your lossless transmission line. Just let me redraw the diagram of a two-way transmission line again. So this is the conductor 1, this is conductor 2, and this is the dielectric medium between them. So this conductor has infinite conductivity, and the conductivity of this dielectric is almost equals to 0. So such a transmission line will be called as your lossless transmission line. For such a transmission line, the value of R and G both are equals to 0. Okay, so if we try to calculate the value of gamma, which is nothing but square root of R plus j omega L into G plus j omega C, so this will give rise to, I'll get gamma value as square root of j omega under root LC. Okay, so gamma will be a perfectly an imaginary number whose value will be j omega under root LC. Okay, so from this value of gamma we can write that alpha will be equals to 0, because in gamma there is no real term is present, so alpha is equals to 0, and beta will be equals to omega under root L C. So these is very important property or important equation related to lossless transmission line, that for a lossless transmission line alpha is equals to 0 and beta is equals to omega under root LC. Also for a lossless transmission line, wave velocity, which is usually represented as using the alphabet u, which is also equals to omega by beta. So this u is nothing but it will be equals to 1 by square root LC. Okay, because if I write omega here and then omega under root LC here, so omega omega will get cancelled out and it will give me 1 by square root LC. Okay, so this will be the value of u. So these are some important parameters related to your lossless transmission line. Next is my distortionless transmission line. A distortionless transmission line is one where attenuation constant alpha is independent of frequency, and your phase constant beta, it will depend on frequency, or I can say it is linearly dependent on frequency. Okay, the condition for a distortionless transmission line is that R by L will be equals to G by C. So for such a transmission line, the value of gamma is ultimately can be obtained as square root Rg into 1 plus J omega C divided by G. Okay, and if we equate it with the value of alpha plus j beta, so what we can get is alpha as square root of Rg, and beta will get as omega under root LC. So if you can see, alpha, it is independent of frequency, beta is dependent on frequency because of the presence of this omega term. Also for this distortionless line, the characteristic impedance value is nothing but it will be equals to under root R by G, which is and it will be also equals to L by C. Okay, and one more thing which I missed is the value of characteristic impedance for a lossless transmission line. The value of characteristic impedance for a lossless transmission line will be Z naught equals to under root L by C. This is the equation of characteristic impedance for a lossless transmission line. And for a lossy transmission line, sorry, for a distortionless transmission line, Z naught is equals to under root R by G, or it is equals to under root L by C. So these are some of the important formulas related to transmission line. We We'll quickly like to summarize what we have studied in this video is that a transmission line is nothing but it is combination of two or more parallel conductors. This transmission line in electromagnetics, it can be considered as a distributed network of R, L, G and C, where R and L are connected in a series configuration and G and C are considered sorry, it will be reversed. This will be my C. Let me use my eraser. So this will be my C and this will be my G. Okay, so RLGC, and if we just focus on a very small length, very small section of the transmission line, then for that transmission line we can get the expression of instantaneous voltage as VZT equals to V naught plus e to the power minus alpha Z cos omega t minus beta Z, and plus v naught minus e to the power alpha z into cos omega t plus beta z. Okay, and for such an small section the propagation constant will be equals to r plus j omega l into g plus j omega c. Then for transmission line line there is one more important parameter, which is the characteristic impedance, which is also equals to r plus j omega l divided by g plus j omega c. Okay, in instantaneous voltage expression this term represents the positive z directed wave and this term represents the negative z direction wave. V naught plus is the amplitude of the positive z directed wave and V naught minus is the amplitude of the negative z directed wave. Now these are the equations related to a lossy transmission line. Transmission line can also be seen as in like two, we can have two common forms of transmission line. One is lossless transmission line. For a lossless transmission line the condition is that R and G will be equals to 0, and alpha will be equals to 0, beta will be equals to omega under root LC, and characteristic impedance Z0 will be equals to under root L by C. And then we also can have distortionless transmission line. For distortionless transmission line it will be R by L equals to G by C, and for this transmission line alpha will be equals to under root RG, beta will be equals to again omega root LC. So alpha is independent of frequency and beta is dependent on frequency, and Z0 is nothing but it is equals to under root R by G, or it is equals to under root L by C. So these are in brief some important formulas related to transmission line, propagation of or expression of voltage on a transmission line, and then some important transmission line types of transmission lines and its important formulas. So we will continue our discussion on transmission line in the next video.